2.1, Chapter 2. We are working with functions, average rate of change. So your average rate of change is going to be, effectively, you'll calculate the net change in an output that was f of b minus f of a, where b is bigger than a. And then you're going to divide that value by the change in the input. So we did a little bit of this in Chapter 1, but we didn't really talk about it as average rate of change. So f of b minus f of a over the difference b minus a. It's your change in your y over your change in your x. And if you're familiar with the concept I put down there, yes, this does relate to slope. But we're not quite there yet. So right now we're just talking about it as an average rate of change because we have data and we're looking at the average rate of change between 2 points. So if I give you an example of the number of rabbits in a cage. So the days I've given numbers because that's how we can distinguish how many days have passed. So if day 1 is Sunday, 2 is Monday, and so forth through 7. And then the number of rabbits that were counted in that cage, say it's at the exact same time every single day. So 2, 4, 7, 3, 5, 11, and 6. What is the average rate of change over the whole week, which means going from Sunday all the way through Saturday? What is the average rate of change? So to do that, right, we want the number of rabbits that we see on Saturday minus the number of rabbits we see on Sunday, and then divide that by the difference in the number of days. How many days are between Saturday and Sunday? Going backwards. So the number on Saturday, right, Saturday is 7, we had 6 rabbits. So we have 6. Minus the number on Sunday. On Sunday we had 2, so 6 minus 2 on top. And the numbers for the days correspond to 7 and 1. So 7 minus 1 goes in the denominator. And then we could just simplify. 6 minus 2 gets us 4. 7 minus 1 gets us 6. So we have an average rate of change of 4 rabbits every 6 days, which we can reduce to 2 rabbits every 3 days as our average rate of change. 2/3 of a rabbit is disturbing, right? We're not gaining 2/3 of a rabbit per day, but we are gaining an average of 2 rabbits every 3 days. Okay? Now, what about the average rate of change from Monday through Friday? Just to solidify that concept, we had, how many do we have on Friday? Friday we have 11. How many do we have on Monday? Monday we had 4. So 11 minus 4 over the difference between Friday and Monday. And Friday was 6, Monday was 2, so we have 11 minus 4 over 6 minus 2, getting us 7 over 4. So between Monday and Friday, we actually had an average rate of change of 7 rabbits every 4 days. That is extremely large compared to the 2 rabbits every 3 days that we had just by shifting a few days. But just so you get a feel for how this is working, right? The data set isn't necessarily linear, so the average rate of change is going to correspond to which points you're comparing and not to the whole data set. Okay? And then from there, we can talk about applications. So the application we will consider is average speed. And speed is your distance traveled over the time that it takes you to travel that distance. So naturally we can talk about this in the context of an average rate of change as your net change in distance divided by the change in time, the time that it took you to take that distance. So for an example, we will look at data of Bob and Jill racing each other on this 5-mile course. So I have data in this table. Time is measured in 10-minute increments, and then the distances are in miles. So their goal is who's going to hit 5 miles first, which you can probably tell from the data who does. But what we can look at is who's faster in the first 30 minutes. So for that, we want to look at where they both were at the 30-minute mark. So Bob was at a distance of 2.5 miles. Minus, of course, the 0 for the start, over the 30 minutes, minus the 0 minutes. So he was going 2.5 miles in 30 minutes, which we can just sort of leave in, we could leave it in this form, or you could reduce it, right? 25 or 2.5 over 30. You're looking at, if that's 2.5 miles in 30 minutes, that's going to be 5 miles in 60 minutes, right? Which means that we're looking at 5 miles per hour. for his speed. And then Jill was at 2.25. 2.25 minus 0 over 30 minutes minus 0. And so we have 2.25 over 30. And that's the same as 4.5 miles per 60 minutes, or 4.5 miles per hour. So the question being, who is faster in the first 30 minutes? Who has a faster speed? Bob has a faster speed in the first 30 minutes. So to answer that question, that would be Bob. Because 5 miles per hour is greater than 4.5 miles per hour. Now, who won the race? Who actually finished the 5 miles first? You can see that Bob finished the 5 miles at 70 minutes. And you can see that at that same time, Jill was at 5.25 miles. So she hit it before the 70 minutes, which implies that Jill actually finished the 5 miles first. So overall, what were their average speeds? Right, we know Jill finished first, so she must have had a higher average speed over the whole course compared with Bob. So if we take a look at that for Bob, Bob finished 5 miles. He started at 0 in a distance of in a time interval of 70 minutes. 70 minutes minus 0 minutes. So he had 5 over 70. Which means that's 1 over 14 in terms of his mile per hour. That's 1 per 14 minutes times 60 minutes per hour. And in that case, you end up with a 60 over 14 for miles per hour. Now, if we reduce that, you have 30 over 7, and from there you can't reduce it any further. Miles per hour. For Jill, we have 5.25 minus 0 over 70 minus 0. So 5.25 over 70, I can't reduce that, but I can multiply that by the 60 over 1 for the minutes per hour. This is 70 minutes, and this is miles. So I have the 60 over 70, so that gives me a 6 over 7. 6 times 5 is 30, and 6 times a quarter is going to get me a 1.5. So that's 31.5 over 7 miles per hour. Both of these are over 7. 31.5 is clearly greater than 30. So 31.5 over 7 is greater than 30 over 7. So that means that Jill was faster over the whole course. The last bit is not very applied. This is the function representation for what we've been calculating. So when you find an average speed, for example, right, you're taking an average of function evaluations or data points. Now in this case, I'm just giving you a function. I'm not giving you context, right? F of x is equal to x cubed minus 3. What is the average rate of change between x equals 0 and x equals 1? You can construct the data, right? You just determine, well, what is f of 0? F of 0 in this case is going to be 0 cubed minus 3, which is just going to equal negative 3. F of 1 will be 1 cubed minus 3, which is just going to be 1 minus 3, which is negative 2. So when I go to find the average rate of change, right, I'm looking at f of b minus f of a over b minus a. So in this case, that's going to be negative 2 minus negative 3 over 1 minus 0. So negative 2 minus a negative 3 becomes a negative 2 plus 3 over 1, which this reduces to a 1 over 1, or just 1. So the average rate of change for this function between x equals 0 and x equals 1 is 1. You can do that with other x values. So what if we wanted to look at x equals 1 and x equals 2? What about that? Then I just need to determine f of 2, so I have that as a comparison. So 2 cubed minus 3, which is going to be 8 minus 3, or 5. F of 2 minus f of 1 over 2 minus 1 is going to be 5 minus the f of 1 was a negative 2 over 1. So that becomes 5 plus 2, or 7 over 1, which gets an average rate of change of 7 between the points x equals 1 and x equals 2. This is just the computational side. Hopefully with the context from the earlier problems you can see how it does connect, but if you were just working with the function, this is how you would be solving for it. Okay?